Just a quick reminder about significant figures. All right. Significant figures. So every measurement, of course, has significant figures that are associated with those. Okay. Once again, all non-zeros are significant. Leading zeros are significant, are not significant. So zeros in front aren't significant. Zeros at the end are. Okay. So, for example, when we look at numbers like this here, zeros at the end are significant. So that's 4. Zeros in the front don't count. So we only have 2 here for this one. 72, that's 2. 72.00. Zeros at the end count. Zeros in the front don't. Okay, so that's 4. All right. We did this on Friday as well. So when multiplying or dividing, fewest significant digits is what you, or figures is what you need to use. So we talked about density equals the mass over the volume. We took 48.12 grams over 50. Okay. We divide those two numbers, of course, so dividing or multiplying, that works out to be 0.9624 grams per milliliter. And remember, we have 3 significant digits here, 4 here, so when we divide or multiply, you have to go based on the fewest. So in this case, we can only have 3 in our answer, so 3 significant digits, 0.962 grams per milliliter would be our final answer there. We'd have to round it to 3 significant digits. Remember, the 0 in the front doesn't count. Okay? If you add or subtract, it's a little different. So if you're adding or subtracting, of course, 21.5, 2.78, 48, and 75.8, okay? You have to go based on the fewest decimal places. Fewest decimal places. So this is 1 decimal place. This is 2. If it was just between these two, so if I didn't have those other ones, if it was just between those two, I could only have 1 decimal place in my answer, yes? Between 1 and 2 decimal places. I've also included this number here. It has no decimal places, all right? And then, of course, I have another decimal place there, so I have 1 decimal place there. This all works out to be 148.08, okay? But because this number here has no decimals, no decimal places, not to the nearest tenth, it's to the nearest ones place, basically, I have to record my answer to the same preciseness as that least precise one. So that works out to be 148 kilograms in this case here. So no decimal places there, no decimal places in my answer. Okay? That's when you're adding or subtracting. Okay? Next, we talk about scientific notation. The first thing, of course, is it is a number between 1 and 10, and a power of 10 are the two things that scientific notation is made up of. So eventually, when we get to, we'll have to use scientific notation today. At some point, somebody's going to tell me it's 25 times 10 to the something or other. That's impossible. It has to be a number between 1 and 10. Okay? So 2.5. 1, 2, 3, 4, 5. So times 10 to the 5th. Just put them there. People can come grab them. You don't have to. You already went and got them, for crying out loud. 2.5 times 10 to the 5th. This one here, 7.865 times 10 to the 1, 2, 3, 4. Okay. We need to use 2 significant digits for these, so we need to record them to 2 significant digits. Looking at 2. Those 2 there, of course, right? So we need to round that appropriately. In this case, it'd be 7.9 times 10 to the 4. Okay? 0.008946, a number between 1 and 10. Okay? That's a number. It has to be a number between 1 and 10. Otherwise, it's going to be marked wrong. 1 and 10. Okay? And then a power of 10. In this case here, we'd actually have to move the decimal 1, 2, 3 places to the left, so minus 3. If we want 2 significant figures, that's what it says right here, by the way, 2 significant figures. If we want that, then I have to look at basically these 2 right here, 8.9, of course. Still a number between 1 and 10. 8.9 times 10 to the negative 3. Wouldn't round this one, of course, because we look at the next number, right, and it's only a 4, so we're not going to round that one. Okay? And then the last one here, of course, would be 5.85 times 10 to the negative 6, I believe it is. Okay. If we're going to look at two significant digits for this question here, for the answer, once again, we're going to focus on 5.8. The next number is 5 or more. We're going to round it up. Okay. So 5.9 times 10 to the negative 6. Okay. And so that's the stuff we talked about on Friday, basically, in a quick version of that. Right. Okay, good. Let's see. Okay, next. We talked about unit conversions. So changing from grams, for example, or moles to kilograms or kilomoles, or millimoles or milligrams or megagrams. And actually the one we added on to here was a mega, which is 1,000 kilos. Okay, so that's another one you have to know. In fact, we're going to use that one today. So we're going to talk about megagrams today, and you'll have to change that to grams. Okay, so remember, mega is technically 3 steps above or 3 places above a kilo. It's 1,000 times bigger than a kilo. So, and once again, if you're going down this chart, you're moving the decimal to the right. Right, it tells you that actually right here, by the way. And if you're going up this chart, you're moving it to the left. Yes? Okay. And every time you move it up or down, you move the decimal right or left 1 spot. Okay. Remember, every one of these is based on a factor of 10. So you're either going 10 times 10 times 10 times 10, moving it over, or moving it left times 10, or divide by 10, divide by 10, divide by 10. If you're going to do 275 grams into kilograms, for example, okay, once again, you have to kind of figure out where's grams and where's kilograms in conjunction with that. So here's grams, 1, 2, 3 steps up to get to kilo, and I'm going up this chart, of course. So that means I got to move it. I'm going from a small unit to a larger one. So I'm going to have to divide by 3. Right? I'm moving the decimal 3 places to the left. There's the decimal there right now, 275. So I'm going to move it 3 places to the left. And that works out to be 0.275 kilograms, right? If you have a smaller unit of measure, kilograms, and you're going to kilograms, you'd expect to have less of that, okay? You got less of a bigger thing, yes? All right. So make sure you know how to adjust those. And then we got to molar mass on Friday. Real quick here, 1 mole, don't forget, is 6.02 times 10 to the 23 atoms, molecules, particles, could be atoms, could be ions, whatever. We'll do that actually tomorrow. When we talk about the molar mass, we're talking about how many grams does it weigh for every 6.02 times 10 to the 23rd, or for every mole of substance we have. And I told you that that number there is actually wrong. It's 65.41 for zinc. So if you look on your periodic table, of course, you can just look these up, right? Carbon is 12.01. Zinc is 65.41 grams per mole. So if you had 6.02 times 10 to the 23 zinc atoms, you put them on a scale, it would weigh 65.41. That's what the scale would say, 65.41 grams. Okay. We looked at, real quickly here, we looked at basically adding these up and calculating the molar mass of some compounds. So don't forget, of course, one of the biggest things, of course, is that we're able to write out these compounds and make sure you're able to figure out the molar mass. So Fe2O3, for example, we would need 2 irons and 3 oxygens. And if you add those up, of course, okay, so 2 times 55.85 for iron, 3 and 16 for each oxygen, you would get 159.70 grams per mole. Okay. When you talk about aluminum nitrate, okay, ionic compounds, aluminum is a 3+. When you think about this, aluminum is 3+. Each nitrate, of course, is a 1-. So remember, that's where swap and drop comes from. We did this in Unit 1, aluminum nitrate. 1 aluminum has to go with 3 nitrates. So if you look, how many aluminums do I have? I got 1. How many nitrogens do I have? I got 3. How many oxygens do you have there? You actually have 9, yes? So don't forget, it is 1 times aluminum and 3 times nitrogen and 9 times oxygen, of course. Okay? So that works out to be 213.01, it says here. And that's what we're going to do a little bit of practice on today here shortly. And I'll give you some time to do that. Per sulfuric acid, we talked about last day, acids you're probably not going to know how to name for right now. That's okay. I'll help you with those for right now. But per sulfuric acid is H2SO5. And that worked out to be, what was the number from last day, Friday? 114? 114.09? Okay, thank you. 114.09. Copper 2 hydroxide, actually I think I remember this one, it's 97.57. Is that right? Grams per mole. Nickel 3 carbonate, so don't forget 2 nickels. You need 3 carbons and 9 oxygens, because the 3 goes to everything inside the brackets, of course. That worked out to be, I don't remember that one. What is that? 2 or 300? Yeah, that sounds right. 297.41. And CBr4, CBr, so 1 carbon and 4 bromines, works out to be 3 something, doesn't it? Yeah, that sounds good. Thank you. 331.61 grams per mole. Okay? So, once again, it's very, very important that we get the right formula with the right molar mass so that we can do that. We're going to add on to that today here right away. So, flip the sheet over. I don't have this on here. You guys got some stuff to fill in. You guys are going to do that right away here. Couple ones that you probably will not know, and that's okay for right now. Unit 3, we're going to talk about acids, but oxalic acid, for example. The first thing about acids is this. Acids are molecular compounds, okay? So this is something we're going to talk about in Unit 3. Acids really start out as molecular compounds. When you put them into water, they undergo a process called ionization. They ionize. And what does that mean? They turn into ions, basically. So all acids ionize or break up and form hydrogen ions. Okay? So all acids will have an H+, basically. That is what makes, the more H+'s you have, the stronger the acid is. And the stronger the acid is, the lower the pH is. And we're actually going to calculate pH this year on some compounds and whatnot. So all acids will have H+. So if you ever see acid, you know it has to have an H+. The oxalic part comes from the ion that's present. Okay? So in this turn, it turns out to be oxalate ion. So if you treat this as H+ and OOCCOO with a 2-, and you do a little swap and drop, because acids, that's how we name them usually, with hydrogen in front and then the rest of it after, that'll give you the formula that you need to use for that. Okay? So acids are kind of unique like that. Hydrogen's always in front. It doesn't actually, well, technically it doesn't have to be, but usually that's how we write them, just for simplicity's sake. So if you swap and drop that, that'll give you the oxalic acid that you need. Aqueous hydrogen benzoate. Aqueous hydrogen benzoate is actually another way to name acids with the aqueous in front. That means it's been placed into water. You don't need to worry about the aqueous part. So this is basically what you're going to do is hydrogen and benzoate. Okay? And I don't remember what charge goes with benzoate. I think it's a 1- if I'm not mistaken. Swap and drop, that'll be your formula for that one. Okay, look up benzoate and that's it. And then the very last one here, when you go to write out the name, HSCN, because H is out in front, I want you to name it like an ionic compound you would. Okay, so how do you name HSCN? Well, I want you to, you can't name it like a molecular compound. We only did naming molecular compounds, we only did 2 atoms, yes? Like dihydrogen monosulfide or H2S or something like that, or CO2 or CH4, yes? That's too many atoms. You can't do that. So we're going to treat this as an ionic compound. So I want you to treat it as H+, and of course SCN must be a 1-. Swap and drop is how you get that formula. So look those up. That would be hydrogen, and then SCN, whatever that works out to be, is how you name that. Okay? I'll let you guys work on those for about 10-15 minutes or so, and we'll go over them and move on. Just a few notes about some of these guys. First one's first, oxalic acid. We've separated so it looks a little more symmetrical here, but H2OOCCOO is just fine. So if you see it like this, or if that's how you wrote it, that's fine. Okay. Hydrogen, what's the next one here? Hydrogen silicate would be okay for the name of this one here. So hydrogen silicate for silicic acid would be fine. And the last one here, once again, if you have aqueous hydrogen benzoate, if the H is out front, that's perfectly fine. Okay. The H is out front, that's perfectly fine. There's nothing wrong with that. So if the H, yeah. And then the rest there, I think are okay there. Okay, so just check those over real quick, and once again, if you have any questions, let me know. Go on here if there's no other questions, I guess. Let's go back to here for a sec, and here. Nope, we'll do that tomorrow. We're going to talk about mass amount calculations, and once again, I'm going to go through this fairly quickly because we did this last year. I'm sure you did somewhere, unless you're like from Saskatchewan or something. Who knows what they do there now, right? But otherwise, you probably would have done something like this, where we compare mass in grams to amount in moles. Okay. Once again, you have to know the units to go with formulas, of course. This is the mass in grams. Okay. So make sure you write that down somewhere. Please do that when I give you these formulas. Big M is the molar mass, and that's represented as grams per mole. Okay, are the units that go with that. And N refers to the amount. Okay, please make sure that when I ask you a question like what is the amount, that you know what you're finding. Okay, it is obviously the moles. How many moles do you have? What is the amount of this substance? Which is another word for saying moles. What is the moles for this substance? Okay? Because I'm going to ask you a question at some point, probably in the near future here on a quiz. I'm going to say what's the amount of this, and people are going to try and give me the mass. And if I want the mass, I'll ask for the mass. Okay? I'll say, what's the mass? I don't want the mass. I want the amount, the moles. Okay? That's what the amount refers to. So, simply put here, we're going to use this formula, of course, N equals little m over big M. We are looking for, in this particular example, the amount, so we're looking for N, of calcium carbonate would be equivalent to a mass of 27.5 grams. So 27.5 grams is my mass. What's the molar mass? Well, I have to figure that out, calcium carbonate. Okay, so I'm going to write that down over here, calcium carbonate. These are all the things that I would expect when I'm giving you a quiz, or I expect for your homework for tomorrow when I check. I don't want to see just answers tomorrow. I want to see some work. Okay? How are you getting N? Are you copying it from your neighbor, or did you actually calculate it? Do you have that number somewhere? Okay? So I don't want to see answers from now on. I need to see work. Okay? Calcium carbonate. Calcium's what? 40.08, I think. Carbon's 12.01, and 3 oxygen, so that's 48, so 100.09 grams per mole. And when we divide those two, yeah, I did 2 plus, 2 minus, and reduce. Yeah, and reduce. 27.5, and you know that brings us back. If you don't reduce, what happens? You actually end up with twice as much as what you're supposed to, right? And that's bad, because you're going to get way less moles than what you're supposed to. All right, 27.5 divided by 100.09, and I get 0.2747527 and of course that would be measured in moles. Okay. Quite often you're going to see me do this, and just so you know, this is what I do. I write down the first 2 or 3 numbers, whatever I need, kind of thing. And then I just put some dots behind it to indicate that that number goes on for quite some time, probably. There's quite a few numbers on there. I don't need to write them all down, okay? What I ultimately need to do is, if I'm going to use this number again, which we will tomorrow, so tomorrow we're going to take this number and do another thing with it, and then another thing with it. So yes, tomorrow I want you to use the unrounded number. If you want to write that number down, go ahead, but I don't think you really need to. There's a lot of numbers there. Keep it on your calculator, though, for tomorrow, and then tomorrow you'd apply it again and apply it again. You'd round at the very end, of course. Today, this is all we need to do, what amount, so we're done here. You do need to round and use significant digits. So I have 3 significant digits there, yes, and I have 5 down here for my molar mass. So there's 5 and there's 3. I'm dividing or multiplying, so I have to go with the fewest significant digits, yes. So my final answer here would be 3 significant digits. Wouldn't be a bad idea if you circled it or underlined it or something like that, so I know that that's in fact your final answer at some point in time. Otherwise, I got to go on a scavenger hunt, and I don't really like those. I tend to pick the wrong answer for you. I'm bad at picking the right answers. I'm not good at it. So 0.275, 3 significant digits, okay? Remember the 0 in the front doesn't count, so 0.275, 3 significant digits, because I have 3 and 5 in the question, I have to go 3, yep. This one here, what is the mass, okay? So once again, I want to start with this formula here. You know, as I told the other periods today, honestly, guys, at this point in stage, I don't know what to tell you. I know how I solve this. It may not be how you solve it. I don't know. I like to I cross multiply pretty much everything I can in my life, because that's how I did it back in grade 5, kind of thing, and that was about 5 years ago. So I kind of stick with that because that's what I know. So I put this over 1 and I cross multiply. I don't care what you do. Some of you guys would say I'd multiply this. If I want to get little m by itself, I multiply this by m, yes, big M, and multiply this side by big M, and then that way those two cancel, and I got little m by itself. Like I said, I don't know what you guys do. I have no idea. I do this, and I cross multiply. 1 times m is m, and then n times big M. Ultimately, I don't care. Yeah, do whatever you got to do. This is the formula we need to work with. Okay, so you need to get that somehow, and I don't care how. This is grade 11. I'm not going to tell you you have to do it this way or that way. I don't care. People have told you that I don't care how you got the answer as long as you show me all your work. They lied to you, because we care about the right answer here. So that's important. So if you're multiplying, or if you're dividing and you're supposed to be multiplying, or vice versa, that's not going to get you the right answer. Okay, this is what we need to be focused on here. N, of course, is 0.0027 moles, and molar mass, okay, big M, is zinc phosphate. Well, zinc phosphate looks like this. Once again, if you can't get the right formula, this is not going to work out well for you, yes? Because your answer is going to be wrong. I'm telling you right now. Zinc's a 2+, phosphate's a 3-, yes? So swap and drop, right? And this is step 1 of about, well, eventually 7, yes? So this is important. You get the wrong formula here, everything else is wrong, yes? Zinc phosphate, it looks like that. 2+, 3-, swap and drop. So I need 3 zincs, 2 phosphoruses, and 8 oxygens, yes? So let's do that. 3 zincs, 2 times 30.97 for phosphorus, and 8 oxygens at 16 each. That's 386.17 grams per mole. So my mass is equal to 1.042 grams, yes? And so on and so on. question now becomes, okay, what am I going to record in the numerical response thing on my test someday? And the answer is, well, significant digits, yes? So when we look at this, I say, well, how many significant digits do I have here? And the answer is how many? 2 is the correct answer. Zeros in the front don't count. How many do I have over there? 5, yes? So how many do I have to have my answer? 2 is the correct answer. So my final answer here would be 1.0 grams would be the mass that I would expect to have there. Okay? If you take 1 gram of zinc phosphate, measure out 1 gram, that would be equivalent to 0.0027 moles of zinc phosphate. Okay? Yes? Questions, anyone? All right. So, moving on here. And the last one here, last example. It says here we have an unknown chemical. It's examined. It's 3.86 moles is what that says. It should say that on your sheet there. I kind of wrote over it. And it has a mass of 275 grams. What is determined its molar mass? And molar mass, of course, is big M. And once again, I don't care how you do this. I'm going to do my own thing here. And if you don't want to pay attention, that's fine. Cross multiply. I get that first of all. And then if I want to get big M by itself, I would divide by N, divide by N. And like I said, I don't care what you do. But ultimately, at this stage, we should all have this formula here. Okay? Like I said, right? You've probably solved for variables since grade 9 or 8 or 7. I'm probably not going to change the way you do it now. And I don't want to. Okay? But that's what you need to end up with, however you wish to. Okay? The mass, I was told, was, I forget, 275. And the moles that are equivalent to that are 3.86 moles. Determine its molar mass, yes? And look, when you think about this, molar mass is measured in grams per mole. Look, grams per mole, yes? That's what I have here for units. We should include units as well, by the way. And I get 71.2435 grams per mole. That number keeps going, by the way. And then once again, you want to consider significant digits. Now, yes, when you look on the periodic table, they're always going to have 2 decimal spots. So you're always going to have, when you add them up on the periodic table, all the elements on the periodic table have 2 decimal spots, guaranteed. Okay, except for lead, but you can just assume the last one's 0. But that's not the case here, because I'm not using the periodic table to find the molar mass. I'm using a formula. So I need to go based on, once again, significant digits, significant figures, right? So this has got 3. This has got 3. I probably should have 3 in my answer, yes? So 71.2 grams per mole would be my final answer here. Okay? Yes? Okay? And yeah, so that's pretty much all we're going to do today for that. Just a few things I'm going to mention on the next sheet before you get started here. And you'll probably get this done before you go home today. So just a reminder, like I said, you solve these for however you wish to. I'm not going to tell you something different right now. If you want to do this and you're not sure, then go ahead and do that. I don't care. But we need to make sure we get the right formulas. Some students want to, memorize these 3 formulas. Well, there's nothing wrong with that. But what happens when you get to the 5 variable one? Are you going to memorize all the possible combinations for that? I guess you could. Personally, I don't think so. I think we should just use some math and solve for those, but it's up to you. Some people use triangles and stuff, and circles and squares and octagons to solve these formulas. You know what I'm talking about? The triangle thing, right? Well, that's fine, and that works fine, whatever. I don't care. But just remember, we're going to get to PV equals nRT, 5 variables. I don't think that works in, there's 5 things, that doesn't work into a triangle very well. So I don't know, probably just better off to know how to solve these. And if you need practice with that, come see me. But like I said, that's something I assume that we can probably do by now. Okay, a couple things here real quick. Things that you're going to run across here real quick. You're going to run into a megagram today. Remember, that's a megagram. And don't forget, that's 1,000 times bigger than a kilogram, yes? Which is 1,000 times bigger than a gram. Okay? You're going to have a little mg, which is, of course, the milligram, is how you're going to know the difference between those. Yes? So, make sure you convert that back to grams before you put it in the formula. You're going to run into something called a kilomole. You might say, well, actually, here. You might be tempted to go out to the farm and do that. Well, true, but this is a kilomole. It's 1,000 times bigger than a mole. No one got that joke, apparently. Mole's an animal. Spelled a little differently. Never mind, just go back to bed. Kilomole. Get it now? Sometimes on the farm you may wish to do that. They're very good at digging holes. You know how you, this is kind of off topic here. You know how you go, is once again 1,000 moles, yes? So you have to convert that back to moles. Don't forget that when you're talking about, one more thing after this, guys. When you're talking about this formula, make sure you use grams per mole, and moles into this formula. Don't try and put kilograms into there. I would strongly advise against that. If you do put kilograms into there, you will eventually have to convert it to the appropriate grams. So you'll have to use a factor of 1,000 eventually at some point in time. Okay, so don't forget that. Hey, just a real quick question, or something I should mention here. Let's say you had a 0.19, and I'm going to be silly here. 4, 3, 2, 1, and you multiply those two together, which gives you, by the way, let's see here. Bear with me for a second. 820.99. Okay. How many significant digits do you have in this question here? How many are here? How many are here? 4. So how many can you have in your answer? 2, correct? So how are you going to represent this as 2 is the question. And the answer is there is only one way you can do that. And that's why we do scientific notation. Yes? Okay, because there's, even if you round it to 821, which most of you guys are looking at that and kind of itching to do that, that's still 3. You got to get it down to 2. The only way to do that is to use scientific notation. 8.2 times 10 to the 2, 820. Yes? But with scientific notation, the only numbers that are significant are those ones there, of course. So you will have to use scientific notation. I'm going to tell you that's going to happen to you a lot in the next 3 units, because that's what it is. Okay? That's why we mentioned it. So, good? Yes? I'm going to be quiet. You guys can do work. How's that?